In the last lecture, we have learned about the continuum approach, and we have understood that by considering such a continuum approach, how we can study or how we can analyze the different fluid systems and how we can define the properties of fluids by the use of concept of continuum. So to start with, first we'll consider a property of mass density. So mass density, it is denoted by a Greek symbol rho, and it is defined as the amount of mass contained within a unit volume. So mass per unit volume, it is nothing but mass density. So we can say mass density, it relates the mass contained within a volume of a substance. So here we can consider two different cases. So in case number one, we can observe here that the mass contained within a volume, it is large. So these are nothing but the molecules contained within this volume. So these molecules together will constitute the mass. So the mass contained within the volume that we are considering here, it is very large. So we can say the mass is large divided by volume. So mass upon volume, it will give you a larger value, and hence we can say this is more dense material. In the second case, the same volume we have selected, but now here the amount of mass contained within this volume is very small, and hence from this we can find out that mass is less, volume is remaining same, so mass upon volume will be a smaller quantity, and hence we can treat this material as a less dense material. As we have understood what exactly mass density and how it relates the amount of mass contained within the volume, now we'll understand exactly for liquids and gases how this mass density is going to behave. So we know ideal gas equation. So PV is equal to MRT, it's ideal gas equation. So this R is a specific gas constant. It's known as specific because it is a gas constant for a specific mass of gas we are considering. So P is pressure, V is volume, M is mass, R is a specific gas constant, and T is the temperature. And this constitutive equation, it is known as the ideal gas equation. So now if we rearrange some of the terms within this equation in some manner as it is shown here, so transferring this M towards LHS and this V in the denominator, so it will become P upon M by V. So this mass per unit volume, it is density, and this equation will get reduced to P by rho equals to RT. So this equation, it clearly shows that rho, it's a strong function of temperature as well as pressure. R is a gas constant, so we are treating this as a constant. So rho depends on temperature as well as pressure. Now if we consider that in a system, in a gas system, if temperature is increased, now what will happen? As we are going to increase the temperature, it means that it is giving certain energy in. So because of this, the gaps between the molecules will go on increasing. So as the gaps increase within the same volume, now the less number of molecules will be present, and hence the density will go on decreasing. But when we are applying pressure onto this system, that is we are pressurizing this system from all sides, more molecules will get contained within the same volume. So molecules will get pressurized to enter into this volume, and the number of molecules here will increase. So mass is going to get increased when we are pressurizing this volume. So rho is nothing but going to get increased when we are increasing the pressure. But in case of liquids, the same thing will not happen, because in liquids what we have, a larger number of molecules close to each other we have. So because of stronger intermolecular force of attraction as compared to gases, the molecules are close to each other. So though we are applying pressure, there are no gaps actually present, so that the molecules will get compressed and they will come again very close to each other. And temperature, it is not going to affect that much as in case of gases. That's why in case of liquids we can say that the density is not a strong function of pressure and temperature. Now looking towards units, so in SI system, mass is denoted by kg and volume is meter cube. So unit for mass density is kg per meter cube. As we are following SI system throughout this subject, that's why we are considering only SI system here. In CGS, mass will be in grams, volume will be in centimeter cube. Now what are the dimensions of this system? So mass in MLT system, it is denoted by M. Volume, it is length cube, so it will be M upon L cube, that is M L raised to minus 3. And here we are defining density rho, based on the continuum approach, that is delta V. It's a very small volume, and within this small volume certain small mass delta M is present, and this small volume delta V, it is tending to x cube. So this x cube is a critical volume, it is not tending to 0. So that we have already covered. Now next is weight density or specific weight, which is denoted by small w, or it is also denoted by gamma, which is a Greek letter. Now how this weight density is defined? So weight density is defined as weight per unit volume. So mass density was mass per unit volume, and this weight density is weight per unit volume. So weight we know it is equals to mass into acceleration due to gravity. So mg upon v. So but this m upon v is nothing but what? Mass density rho. So we can give this equation as weight density equals to mass density multiplied by acceleration due to gravity. Now why we are defining this weight density? Though we have mass density, but why there is a necessity to define this weight density? It's because when solving most of the problems in fluid mechanics, you will come to know that rho and g, this multiplication, it is coming in most of the cases, and because of which instead of using two different parameters, we are using a single parameter, which is w, small w. So multiplication of these together, it is known as a single parameter, small w, which is nothing but weight density. Now what are the units of weight density? So weight, it is in Newton, and volume, it is in meter cube in SI system. So unit will be Newton per meter cube. Dimensions will be, so force, Newton is a force, so force will be mLt raised to minus 2. This m cube, meter cube, will be L raised to 3. So when you transfer this L cube in the numerator, it will become m L raised to minus 2 T raised to minus 2. Now the next property, it is relative density, which is also known as specific gravity, and it is denoted by symbol S or Sg. So Sg stands for specific gravity. Now what is this relative density? So the name itself, it defines what is the meaning of it. So relative density is nothing but the density of a liquid that is defined relative to some another liquid. So it is defined as density of liquid at any temperature divided by density of water at 4 degrees Celsius. Now instead of defining the density of a liquid with respect to any liquid, we are considering here a standard liquid, which is water at 4 degrees Celsius. So every time when you are defining specific gravity of any of the fluid, any of the liquid, you will define it with respect to water density. So density of a liquid at any temperature you can consider, but for water it is considered at 4 degrees Celsius. So specific gravity, it's a ratio of density of liquid at any temperature to the density of water at 4 degrees Celsius. Now what are the units of it? So as it is a ratio of two densities, it will not have any units, and definitely it will be a dimensionless quantity. Now, as we understood what the meaning of relative density or specific gravity is, we'll understand the physical significance of it. So let us consider I'm having a liquid whose density is 850 kg per meter cube, and water density at 400 degrees Celsius is 1000 kg per meter cube. So 850 upon 1000, it will give you a value of 0.85. Now what is the meaning of 0.85 specific gravity? So it tells us that the liquid that we are considering, it is 85% as dense as water. Let us consider another example in which I am having density of liquid as 13,500 kg per meter cube, which is nothing but a density of mercury. So 13,500 divided by 1000, it will give you 13.5. Now what is the meaning of this 13.5 specific gravity? It means that the mercury is 13.5 times heavier than water. Okay. And 0.85, it means that the liquid is 15% lighter than water. So definitely the lighter liquid will float on water, whereas the heavier liquid will sink down and water will flow onto this heavier liquid, float onto this heavier liquid. So we can consider here one illustration of this specific gravity. So now let us consider in a container we have water. Now we are taking some material which is having a density of 600. So 600 divided by water density will give you specific gravity of 0.6. So when you put this object within this container which is having water, so the meaning is only 60% of this object will get submerged within the water. So 60% will be submerged, 60% will be underwater, and remaining 40% will be floating. So this is the meaning of specific gravity. Now let us consider, we are considering a block having density of 2700 kg per meter cube. So 2700 divided by 1000, it will give you specific gravity of 2.7. So 2.7 in percentages, it means 270%. So it means that 270% it will be submerged within the water. But submerged submerging can be only up to 100%. It can't exceed 100%. So what we can say related to this 270%, we can say that 100% of the block will get submerged within the water. So it will get submerged and it will sunk down. This is the significance of specific gravity.